300 cubits long, 50 wide, 30 high, 3 decks, 1 door, 1 roof opening finished to a cubit, gopher wood, and pitch spread inside and out. That is the complete specification from Genesis chapter 6, roughly 137 meters by 23 by 14, depending on which cubit you trust. Those numbers describe a hull at the outer edge of what timber shipbuilding ever managed, and beyond it if the whole Genesis length is treated as working hull. No keel, no rudder, no mast, no sail, no bow, and no stern, nothing that would make the thing move through water and nothing that would let it steer. Everyone knows what Noah's Ark looks like, a wooden boat with a high prow, a rounded stern, and the neck of a giraffe poking through the roof. Almost none of that comes from the text. The specification reads like a granary or a livestock barn tipped onto the waterline and sealed shut. The question this episode asks is why the Hebrew account gives exact dimensions, but a structure no shipwright could build in wood. A hull with no way to move, no way to steer, and no feature that belongs to any vessel designed to survive open water. The Genesis hull is not the oldest version of this object. It belongs to a wider ancient Near Eastern flood tradition, and the surviving versions specify different containment solutions for the same problem. Keep a sealed load above the waterline. In the Atrahasis tablet, the oldest of the three, the vessel is a coracle, a vast round boat made of woven rope sealed with bitumen, like the reed boats that still crossed Iraqi rivers into the 20th century. The tablet specifies how much rope and how much bitumen, as if the builder were placing a material order. A circle distributes load evenly across its hull. There is no weak axis, no bow or stern to concentrate stress. It is a basin, and a basin does not flex the way a long hull does. In the Epic of Gilgamesh, several centuries younger, the survivor Utnapishtim builds a hull with equal sides and 7 decks. The thing is a cube, a warehouse that could be stacked floor on floor, with no feature that distinguishes one face from another. Among rectangular boxes, a cube encloses a given volume with the least surface area, and by dividing the interior into 9 compartments, the Gilgamesh text limits the free surface of any water that enters, which a naval engineer would recognize as a basic flooding precaution. And then the Genesis text, later still, lays the object out as a long rectangle. The cube becomes a barn set on its side, low, broad, 3 decks deep, where the coracle avoids stress by having no long axis and the cube distributes it equally in every direction. The Genesis box concentrates it along 137 meters of timber, and that length is the source of almost every problem that follows. The 3 solutions are not interesting because one text borrowed from another. They are interesting because a circle, a cube, and a long box are 3 structurally different answers to the same containment problem. The coracle holds by surface area. The cube stacks by height. The Genesis box stretches by length, and in doing so, it runs straight into the one material limit that the other 2 geometries avoid, because a timber hull 137 meters long will flex across the waves until its own joints pull it apart. Take the Genesis hull at face value. 137 meters of timber, 3 decks high, rectangular in cross-section, no curvature. What you have is a pure hold, a box built for volume, with nothing in its form that belongs to a vessel meant to travel open water. The first system that fails is the hull itself. Timber flexes, and a hull this long rides across wave crests rather than rising and falling with them. As it spans the gap between 2 crests, the center bends, upward when the crest is amidships, downward when the hull sits between 2. Naval engineers call these motions hogging and sagging. Past roughly 90 to 100 meters, the bending forces exceed what historical timber hulls could manage without metal reinforcement and constant pumping. The fastenings, pegs, tenons, lash joints, whatever method holds the planking to the frames, are being asked to resist forces that rise quickly with the hull's length, and thicker timber does not remove the problem once the whole structure starts working as a beam. The seams between planks begin to work open under the repeated flexing. Seen in section, the timber is bowing across the wave, and the gap between planks at the stress point is widening with each cycle. This is not a theoretical limit. The 6-masted schooner Wyoming, launched in 1909, was about 110 meters long and needed iron cross-bracing throughout her frame to hold her form. Even so, her seams worked open in heavy weather and her crews pumped her continuously. In 1924, she went down in a storm off Nantucket with all hands. The Genesis hull exceeds that working wooden hull by nearly 30 meters. Without anything like Wyoming's steel bracing or steam-powered pumps, in a storm described as lasting 40 days. The pitch the text prescribes, applied inside and out, is the right response to a hull you do not trust to hold water on its own. Bitumen was the standard Mesopotamian waterproofing, and doubling the coating on both faces is a plausible response for a vessel expected to sit low in the water for a long time. But pitch seals a joint that holds still. On a hull this long, every joint moves a little with every wave, and a sealant that cracks under flex is being asked to do something it cannot sustain over 40 days. The second system that fails is the enclosure. The named side door has to serve as the loading opening and then seal shut against the water. A door is a joint, a rectangular hole cut into a load-bearing wall, framed with timber that has to carry the hull's stress around the opening while also seating flush enough to keep the water out. On a hull that is already flexing past its limits, that frame is working with every wave and the seal degrades. Once closed, that door becomes part of the hull envelope for the rest of the voyage. And then the air. The Hebrew text gives one sohar, a roof light or roof opening finished to a cubit, depending on how the word is read. That is not a ventilation plan for 3 enclosed decks of living cargo. Heat, moisture, and foul air accumulate in any sealed space, and the rate depends on what is breathing inside it. Even a well-ventilated stable needs deliberate airflow. Seen in section through the 3 stacked floors, the lower decks are the farthest from the one opening near the roof, and what those floors produce in heat and foul air has no obvious path out. The hardest problem in this specification was never the storm outside the hull. It was the 3 enclosed floors of warm, breathing cargo, with a single ambiguous roof opening asked to serve as lungs for the entire hold. Every system in this hull strains or breaks something: the timber, the joints, the enclosure, the ventilation. But there is one number in the specification that does not break, and it is the number that changes everything. The Genesis dimensions give a length-to-breadth ratio of 6:1, 300 cubits long, 50 wide. That is not a ship's proportion. Sailing vessels and warships tend toward ratios of 8, 10, 12:1 long and narrow, built for speed and maneuverability. A 6:1 hull is a barge, broad and flat and slow. The length-to-height ratio is 10:3, again broad and shallow, a low profile sitting in the water rather than rising above it. Published stability analyses of these proportions find that the hull is surprisingly hard to capsize. The hull, loaded to a plausible draft, carries a low center of gravity and a wide beam. When a wave strikes from the side and rolls the hull, the righting moment, the force that pushes it back upright, is strong and returns early. Drawn in section with the waterline marked and the center of gravity plotted against the center of buoyancy, the geometry shows why. A broad, shallow, heavy box with a flat bottom resists rolling the way a raft does, sitting so wide and so low that the lever arm favors the upright position. The text is not describing a ship. It is describing a building that floats, a long timber box that cannot go anywhere, cannot steer, and will probably destroy itself in a heavy sea, but that will sit level under load for as long as the wood holds. Whatever route brought those numbers into the tradition, the specification preserves the ratio that keeps a loaded hull from rolling onto its beam. Stand back from the full reconstruction and look at it whole. 300 cubits of gopher wood, pitched inside and out, 3 decks, 1 door, 1 ambiguous roof opening, a hull too long for its timber, too sealed for its cargo, and too broad to capsize. What survives in the numbers, after you strip away everything the hull cannot do, is a single ratio, buried in a list of cubits, that answers a question the text never openly asks: which way does a heavy box fall when the water rises? The hull cannot sail, cannot steer, and cannot survive its own length in timber. But somewhere inside Genesis chapter 6, a working proportion remains, and that single piece of engineering has been sitting in the specification for centuries. If one right number can sit in plain sight inside an ancient specification. The question is what else is sitting in the other ones.